Thank you for joining us for the Consulting Specifying Engineer webcast, Critical Power, Generators and Their Design, sponsored by ASCO. I'm your host, Amara Razgis with Consulting Specifying Engineer and CFE Media and Technology. Let's learn about this webcast platform. If you're having trouble with your slides or the audio, please click on the Refresh Media button directly under the presenter's photo or refresh your internet browser. You can control the volume settings by adjusting the volume on your own device. If you're having technical problems, click on the question mark at the top right corner of your screen to do some system checks before contacting an online technician. If you do need help, please type a question into the Ask a Question box and we'll respond in the Answered Questions box. To download today's presentation, use the Event Resources on the left side of your screen. Please type questions for the presenters in the Ask a Question box on the left side of your screen. You may ask questions at any time during this presentation. The interactive Q&A starts in about 45 minutes. If you're interested in receiving one AIA CES approved learning unit for this event, you'll have to pass the 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab at the top of your screen. The quiz will open in a new browser window, so I recommend you open that tab right now because the link will break when this webcast signs off. In keeping with the American Institute of Architects Continuing Education System Policy, please take a moment to read this quality assurance slide. So here are the learning objectives for today, and we'll talk about this in today's presentation. Anything that is blue and underlined is a hyperlink in the PDF where you can get more information. All right, let's now hear from the sponsor. At the conclusion of the commercial, you may experience a few seconds of silence to make up for varied internet speeds. Please stay tuned after the commercial for today's presentation. All right, well, thank you so much for that support. We've lined up two really informed presenters today. Dana Jensen is one of the founding principals of Certus Consulting Engineers. With 20 years of experience in the consulting engineering field, she has extensive experience in the design of reliable and efficient electrical systems for complex healthcare projects. She brings large-scale technical expertise and innovative concepts to her role at Certus, where she focuses on advancements in engineering and technology. Dana was a Consulting Specifying Engineer 40 Under 40 award winner, and she is on the editorial advisory board. James Lessard is with Canon Design, and he's based in St. Louis. James is an electrical engineer with 15 years of experience providing engineering consulting services to both public and private sector clients. He has extensive experience preparing lighting, power, communications, fire alarm systems, and security improvements for a variety of projects and clients throughout the United States. These include healthcare, higher education, government, industrial, K-12, and transportation and infrastructure. James is well versed in the pursuit of energy efficiency and sustainability initiatives, and the pursuit of LEED and other types of accreditations. All right, James, you're up first. Let's get started.
Oh, thank you, Amara. It's good to be here with everyone today. So Dana and I wanted to structure the presentation similar to the way in which the process that you would follow as you're designing a system. So that's kind of the trajectory of the presentation today. First and foremost, we want to talk about local codes. The authority having jurisdiction, the jurisdiction in which you are working oftentimes has a series of codes that they've adopted, national codes. And here's a sampling of those, the ones that you would typically find. So the building code, for example, you could be surprised by the requirements that are applicable to generator installations in the building code. But Chapter 27, which is the electrical section of the building code, has a significant amount of requirements for things like room partitions around your generator, or the runtime of the generator, or the transfer duration when you have a loss of normal service, etc. The life safety code, as the name implies, the code deals with things pertaining to the preservation of human life. You'll find a requirement in there for 90 minutes worth of runtime on illumination for egress path and exit signage throughout the building. Of course, you're all familiar with the National Electrical Code. Articles like 700 for emergency systems, 701 for legally required, 702 for optional standby, 705, 708. And then in the case of healthcare, where you've got Article 517 specific to healthcare installations, which also references NFPA 99, which is the code for healthcare. There's a lot of code implications. There's a lot of code research required. It's important that you do that study, early, and that you kind of follow that process throughout the process that you're revisiting the code requirements. The fire code also is one that's often applicable in the mechanical code that deal with things like the fuel piping into the building, exhaust, intake of air, ventilation, etc. And you'll find often that there's a lot of overlap between these codes, and there's not always a guarantee of finding that the codes always agree with each other. The most stringent always applies, but it's important that you understand what each code brings to the requirements. And then in the case of local amendments to codes, you'll find that the jurisdiction often they'll amend the codes either by replacing or deleting or adding to. In this example from Fort Worth, Texas, they've done that to the 2017 edition of the National Electrical Code. So beyond the local code requirements, you'll also have standards that apply, right? So NFPA 37, which is the standard for installation and the use of stationary combustion engines and gas turbines. The scope of NFPA 37 is really written around the prime mover portion of the generator. It's the engine itself, right? It covers things like install, maintenance, operation, and testing of that engine. It doesn't care about the electrical aspects of your system. It doesn't care about the alternator. It doesn't care about the transfer switches downstream or the associated distribution. It's really related to the fuel supply, the tanks, the environment. NFPA 110, absolutely a staple when you're designing a generator system. It's the standard for emergency and standby power systems, and it introduces a few things, including classifications, types, and levels, which we'll get into a little bit more in detail here in the next few slides. But it's important to understand what those are. Class and type apply to the emergency power supply system, which is the transfer switch equipment, and not necessarily the generator, which is referred to as the emergency power supply, or the EPS. NFPA 110 covers everything from installation, maintenance, operation, and testing of the entirety of the system. There's a lot of overlap between 110 and NEC and some of the other codes. So it's important to understand these standard requirements as well. Additionally, it's important that we understand what the occupancy of the use is, whether we have a healthcare facility, because it's going to drive exactly what the requirements are in code. NEC 517, NFPA 99 are directly applicable to healthcare, but they're not necessarily applicable, or they wouldn't be applicable to mission critical facility, for example. That might fall under NEC 708 as a critical operation facility. Data center falls into, 640, 646 of the NEC. Various codes have requirements for high rises, buildings over 75 feet above finished grade. So it's important that the occupancy is understood and that we understand how that impacts, the various applicable sections of code. So let's take an example here, healthcare example. Again, NEC Article 517 kind of governs the requirements for the electrical system in a hospital or other healthcare facility. Specifically, it introduces the essential electrical system, which requires, 3 separate branches of distribution, the life safety, critical, and equipment branches, unique to healthcare installations. It also references, in many cases, NFPA 99. And so it is really the how to implement 99. It's kind of the instruction manual to follow to meet the 99 requirements. And NFPA 99, which is the Healthcare Facilities Code, is generally consistent with 517. In the past, there were some discrepancies, but they've, through the code revisions, they've worked through a lot of that. It lists the performance criteria. Like I said, it sets the criteria, and then the NEC defines how you implement that. In 99, they introduce the concept of 2 different categories for systems. The first being, preservation of human life. Is there a risk to human life? That would be a Category 1 system, and a Category 2 system is a risk of minor injury. So there's a distinction there, and there's separate requirements for each of those 2 system categories. NFPA 110, again, has a level 1 description of a system that has a risk of loss of human life. So your hospitals would be defined as a level 1 system per NFPA 110. And then in healthcare occupancy, you often have FGI guidelines to contend with as well. Many local jurisdictions, they've adopted this almost, they enforce it as code. So it's important that in addition to the national codes, the local amendments, the standards, that you also follow NFGI guidelines in a healthcare facility as well.
All right, James, before we go any further, I'm going to ask the audience to participate in a poll. And the poll question is, in which building structure do you specify, design, or make product selections the most frequently? So you only get to choose one option here. If you could select one of those options, let us know which one you work on the most. That would be fantastic. I will give us a couple of seconds here to provide some feedback, and we can understand where the answers are coming from. So far, oh wow, we have a couple interesting options here. Looks like hospitals is winning out. Data centers is pretty close behind, and industrial manufacturing buildings is in 3rd place. So the answer continues to be hospitals and healthcare facilities as number 1, and industrial and manufacturing buildings just caught up in number 2 spot. So I hope that helps you, James, and eventually Dana, as we move forward in this presentation. Thank you so much for participating, and let's move on.
Absolutely, that's great feedback. So as we get into generators further, we want to make sure that we understand what the ratings of the generators are. It's important on every project that we define the ratings of the generator specific to your project. First and foremost, NEC sets up an emergency versus a non-emergency classification. If it's serving an NEC Article 700 load, Typically, those are egress lighting, exit signs, fire alarm, those types of loads. Very specific. The NEC defines what loads fall into which article. So that's emergency versus non-emergency. And then you've also got tier ratings, right? So if you're using your generator for prime power production, so if you're using the generator more often than not to generate the majority of the power for the campus or the facility, that would be a prime power installation, whereas a standby rating would be, if you've got the generator only there for use in an emergency situation where normal power has failed and you need to back up emergency systems, that would be a standby rating. Tier 3 applies to standby, and a Tier 4 applies to prime, and those are EPA emission ratings. So the generator just needs to be rated applicable to what you're using it for. Sometimes you'll find in some markets, the utility company will offer a curtailment or a demand response program where they have like different rates structures for peak versus non-peak power. And there's opportunities to save some money by shaving some demand off, during peak hours or whatnot. In that arrangement where you're frequently using the generators to generate power, you're in a prime situation, and you need to be Tier 4 EPA classification, or I should say tier, because below that, NFPA 110 sets up classifications. So this speaks to the minimum runtime of the system. You can see the list here of the classification. So the different classifications have a different minimum runtime associated with the system. The ones we find most often are the Class 48 hours, or the Class X in a hospital setting. Generally translates to 72 hours or 96 hours. It really depends on your local authority having jurisdiction and other applicable codes. And then the type, also defined by NFPA 110, is the power restoration time. So this is the maximum amount of time between when the utility fails and when your standby emergency generator set, your system, backs up the load. So you'll find type 10, 10-second requirement, NEC 700 emergency loads require 10-second transition maximum time, among other types of systems. But this is generally to get you familiar with the types that are listed in 110. And then also you have levels. NFPA 110 defines 2 levels. Level 1, failure of the system could result in the loss of human life. Level 2 is less critical, as where a minor injury may be sustained. So this is it's important that we understand what our level, what our type, what our classification, what our tier is early on in the project.
All right, I think that's my cue. Thanks, James. I know codes are awfully extensive, and boy, you sure know your stuff. So thanks for that. But now we're going to jump right into understanding how we size the generators. We've got the code requirements, we've got the classification. So let's talk about how we size them. The first step is to really understand the types of loads that will be connected to the system and the size, or the impact that they'll have on the sizes. So motors, nonlinear loads, medical imaging, HVAC compressors, VFDs, even regenerative elevators, they all have to be analyzed. Whether they are inductive loads or resistive loads, they have different impacts on the sizing of the system. So for instance, inductive loads, which are mainly motors, obviously are going to slow down or stop when you lose power, right? So bringing them back online as they connect to the generator causes some power transients due to the high inrush currents that exist when they start. This in turn causes a voltage dip. So by contrast, nonlinear loads such as VFDs or computers, they really create harmonic voltage distortion. So this is different from the voltage dips and transients that the inductive loads create. Rather than nonlinear loads, they generate the harmonic currents, which flow through the alternator's source impedance. And then again, even regenerative elevators must be considered since they exert energy back into the system. A typical generator can assume around 10% of a nameplate rating of regenerative load types. So you really need to ensure that your generator is large enough to handle those types of loads, or you have to guarantee that there's going to be enough loads connected to the system for that to be able to use the power so that it doesn't negatively impact your generator. So through a thorough review of all of your anticipated loads, and the load profile will really impact the size of the generator system. The transients or voltage dips that I mentioned that are caused by inductive loads could negatively impact any other loads that are already connected to the system when they're started. And then the larger the motors are, the more impact they will have. So one way to improve the motor starting is by minimizing that generator reactance or upsizing the alternator. Similarly, in order to minimize harmonics, you could add active or passive filtering to your loads, and you also could consider upsizing the alternator to minimize the source impedance. There are also certain sensitive loads in many systems. I know a lot of people said they're working on hospitals and data centers, so you're certainly dealing with sensitive loads there. And those cannot tolerate large voltage drops or frequency dips that are likely to be connected to the system. For instance, you could have a fire pump connected, and the codes dictate that there is no more than 15% voltage drop allowed when the systems come online. So therefore, again, the size of the alternator may need to increase to handle the load. And the sensitive equipment, such as the medical imaging equipment, there's data sheets that say that equipment can only tolerate a plus or minus 2% frequency variation. So with sensitive loads such as these, it may be more prudent to apply a power conditioner or a UPS upstream to help ride through the start of the generator system and protect the loads, as opposed to increasing that alternator yet again. So one of the best ways to size your generator system is to use load sizing software that's available out there. All of the major generator manufacturers have programs in which you can use. They're typically free and available at your disposal. These software have built-in load types in which we've discussed. They've got inductive loads, nonlinear loads, medical imaging loads, the list goes on. And the good software systems also allow you to input various parameters into the system, such as the voltage and frequency drop limitations that we discussed. So once you've defined the load types, you can physically simulate what will happen and the impact that it will have on the size of the generator as you begin to bring those loads online. And one way to do that is to minimize the impact on the generator is to bring them on at different times. So this is referred to as stepped loads, and it basically allows you to connect only a portion of the loads at a time, wait for the system to stabilize, and then bring more loads online as the system permits. This allows you to make the blocks of loads smaller, therefore having a lower impact on the voltage drop that creates transients on the EPSS. So this is what makes those generating software sizing programs so handy, because you can play around with the step loads. You can set the appropriate priorities, you play with the order in which you may want to connect them, and truly assess the loads to ensure that the generator is sized to handle the transients, which again may mean upsizing the alternator. Have I said that yet? So another group of items to take into consideration, in addition to your loads and those impacts, is really the location and application type of where you are going to be. In high altitude climates, the air pressure drop reduces the air density. So this can create problems with the generator if it's not properly designed to accommodate for it. Since the air is crucial for ignition in any type of generator, the low or the high altitude could negatively impact that. So the generators that are properly designed for high altitude may have a larger fan to partially compensate for that reduced heat capacity, or they could be oversized to be able to run cooler under these conditions. Similarly, high ambient temperatures are also associated with low air densities, and they can cause similar ignition problems due to the inadequate air supply. And what this can do is burden the engine, which is pushing itself to deliver the power it was designed to, but with the inadequate oxygen and the high ambient temperatures, it can fail to do so, and in many cases overheat or sometimes collapse altogether. And then it should not go without saying, all of this talk about increasing the alternator size, you do need to take into account what the environmental aspects or the emissions are going to be associated with those larger engines. As James discussed earlier, you're going to deal with different tier ratings based on the size of the engine that you pick. So it does warrant special considerations in the sizing aspect of the system. And again, James also already discussed the application type that could impact your loads. So if the generator is rated for continuous duty and planned for long periods of runtime, well, it must be much more robust and be able to handle those temperature rises and load fluctuations to last for longer periods of time, as opposed to a standby engine, which may not operate nearly as long or nearly as much throughout the year. So ultimately, our job as engineers is to provide a generator system that will support the loads, but also fall within the client's budget. So once we've assessed all the sizing criteria, most of which indicated that a good solution could be to increase the alternator size, we also then need to consider ways that we can reduce the generator size and still meet the criteria. After all, a properly sized generator is going to not be oversized as well. It's going to save the owner money, not only in upfront costs, but on any cost that might be needed for monthly load banks if you don't have enough load connected to the system to support the required testing. And as I mentioned before, harmonics and load transients are big issues that must be dealt with. One way to deal with the harmonics is to provide filters and rectifiers on nonlinear loads. You could include VFDs or soft start motors, which could assist in the overall voltage dip that I talked about, because those will drastically reduce the starting current on some of those larger motors. And then further enhancements would be to consider 6 and 12 pulse drives that will help to mitigate that voltage distortion. Another strategy is to apply an uninterruptible power supply system that will not only provide uninterruptible power to the critical loads, but it also provides the cleaner power through the use of more filters and rectifiers to the loads, making them less susceptible to the voltage dips and transients on the generator. It basically will act as a barrier to ride through those anomalies while it's using its DC power. So these strategies, combined with the many load steps, or plugging in as many load steps as you possibly can, will aid in the overall right sizing of the system. So let's switch gears just a little bit and talk about how to apply generators in a system design and any redundancies that you may want to consider. So first off, we'll hit a little bit more codes again, but any emergency power system that is required to comply with the National Electrical Code Article 700, as James discussed earlier, is also required to have a permanent means to temporarily connect an alternate source of power. So NEC Article 700.3 Part F states that if the emergency system relies on a single alternate source of power, which could be disabled for maintenance or repair, the emergency system shall include permanent switching means to connect a portable or temporary alternate source of power. So this would include any generator that supports your Article 700 systems, hospitals, high rises, and so on. However, this is simply code minimum. The many critical designs may warrant additional redundancies built into the system. There is a careful balance between figuring out the right redundancy and reliability. When you have the space, multiple engines provide more reliability than a single larger engine. Of course, there's pros and cons to everything, and there are certainly some great advantages to having a system with just one large engine and the temporary tap can, as I mentioned earlier, but this is a code minimum design. So first off, this type of system topology typically is a lower first cost. It also takes up less space, and overall, it's just a very simplistic design. But the biggest disadvantage with this arrangement is that you have no on-site redundancy. So even in the event of a failure, you're basically going to have to wait to get a portable system so that you can get your critical loads back online. So contrarily, a parallel system provides advantages since it does provide that on-site redundancy. Other advantages include more ways for that load prioritization and shedding with the different step loads that we discussed earlier. It's also more easily expanded, providing future flexibility. However, the drawbacks include an inherent higher first cost. You're buying more equipment, you get more physical space, and it's overall more complex systems. Also, paralleling multiple generators produce higher fault currents onto the distribution system. That's kind of an entire other webinar in its own. So to reiterate the differences, let's just take a look at a couple of one-line diagrams. The diagram on the left depicts that code minimum design for a hospital as an example. So again, while it's not best practice, some facilities may only have enough budget for a code minimum design. It's basic with a single engine, and it provides the code required manual tap can, and it's the least cost option. However, the diagram on the right shows what a paralleled system might look like. By adding in a second generator to the system, there's a higher level of redundancy. So the second engine can be designed with either the full or partial redundancy, but the engines are paralleled together to share the load. So this type of design does not require that manual connection that I talked about previously, because now there is not a single alternate source of power. All right, I'm going to send it back on over to you, James.
All right, thank you, Dana. So, as we're going through the design process, we want to make sure that we're taking into consideration location. Where are we putting this generator? In the case of structural, which I personally think is probably of paramount importance, if we're installing it on grade, if we're installing it on the 7th floor of a high rise, if it's on the roof on the 22nd story penthouse of a high rise building, I mean, it's important that one, we have solid foundations, but two, that we're designing for consideration of vibration and sound transference into adjacencies, whether or not we have, maybe this is a research building where you've got a vivarium floor above or below or nearby. We want to make sure that we're minimizing propagation of vibration and sound into those more sensitive adjacencies. So an analysis is probably warranted in that case, in conjunction with our structural discipline. On the architectural side, it's making sure that we're addressing the environmental conditions found in NFPA 110, which talks about the rating of the room, protection for fuel lines coming into the building, shafts for exhaust up through a building, so on and so forth. Floodplains. Are we installing a generator, in a basement level that falls within a floodplain? A lot of state and local codes require supporting design to ensure that, if we're installing in the floodplain, that we minimize the risk of damage from flooding, from sewer backups, those kind of things. So it's important that we consider all of that as we're finding a location for our generator. Like we said, the room rating. Both NFPA 110 and the International Building Code both dictate, what the partition type needs to be, or the rating of the partition around a generator room if it's interior to a building. 2-hour enclosure for a level 1 system, which again is the system where, it's all about the risk associated with human life, or a type 2 system, which the risk is more aligned with a minor injury, would require a single hour rated partition around the generator room. In the case of future access for replacement or maintenance, oftentimes you'll see if you've got a generator located in a subgrade level, that you've got an area well or something adjacent to, and that area well may be dual purpose. Maybe that's also the area way to bring in, makeup air into the generator room, and perhaps the louvered wall of the generator room is removable, so you can get that generator in and out in the future as needed. And as it relates to mechanical design, you need to coordinate with your mechanical counterpart for air intake, for combustion and cooling, and also for exhaust. You're going to have, some kind of a muffler on the generator that's above the generator. So there's requirements for, the exhaust off of that. Are you taking the stack all the way up through the building and out through the roof? Where is that exhaust going? How many floors is it? It's surprising how large that duct ends up getting for the exhaust if you go multiple floors up as you get, back pressure on that shaft. I'm not a mechanical engineer, but I know enough to know that that can get somewhat complicated. Again, the indoor fuel requirements. Do you have a day tank in the room? Where's the main tank? Is it buried in the grade outside? There's fuel transfer pumps. There's a lot of requirements that go with a generator that are mechanically related. The fire suppression system. Again, NFPA 110 kind of dictates what that has to be. They prohibit the use of a CO2 system or an automatic dry chemical system. There are some exceptions, but generally that system is a wet system in the generator room. And then also, again, sound consideration, attenuation through the exhaust ducts in and out of the room. Maybe there's some consideration to adding some baffles or something to that element as well. And then in the instance of an outdoor located generator, you'll find sometimes you'll have sound transmission ordinances where, and I know in the state of Illinois, they have very strict requirements about the level of mechanical noise that you can generate at the property line. And so you have to be very cognizant of the ordinances and how far this generator has to be set inbound to the property line to avoid having a certain decibel threshold at that line. Ways to address that would be a critical grade sound enclosure system, and and a weatherproof enclosure when you're outside anyway. There may be other ways to mitigate the sound, and that's where an acoustical analysis would be warranted if you're having trouble meeting a specific ordinance requirement. Again, proper clearances around the generator and access applies whether you're inside or outside. So if you're outside, NFPA 37, which is that it's the standard that deals with the prime mover portion, the engine portion of the generator, it has something to say about getting access and avoiding being too close to the building or combustible materials. So it requires a 5-foot separation between the prime mover and openings of the building, such as doors or windows, and combustible wall materials. There are some exceptions. So if you're looking to do something, a bit outside the box, it's probably best to consult the exceptions and see if there's something that you can apply there. It's also important that you make sure that you know where the exhaust is going, right? You don't want to suck that exhaust right back into the building through the HVAC system. And sometimes you need a bit of an elaborate wind study to determine where it's going and if the prevailing winds are going to blow it right back in. So something else to consider. Other considerations: do you have a unit mounted radiator? Is it mounted strapped right on the front of the engine chassis, or do you have a remote radiator that's up on the building? Do you have to pipe coolant system up through the building, up onto the roof? Something else to coordinate. NFPA 110, dictates very specific testing requirements for your generator system. This requirement falls on the facility, of course. Once the building is occupied, code NFPA 110 dictates a monthly test, a 30% kW rating of the generator. You're not always able to accomplish that. Maybe the actual building load doesn't reach that threshold. And so, maybe you bring in a portable load bank. Dana touched on that, the need to provide provisions to be able to tie in a temporary load bank. There's also the option of doing annual testing. And again, if you're using a load bank because you don't have the building load to actually transfer and meet these thresholds, or you'd rather avoid the outage, the blip in power, specifically in healthcare occupancies or other critical facilities, it's probably best to provide provisions for a load bank, or provide a permanently installed load bank, right? You can always provide a permanently installed load bank that's either radiator mounted on the front of the unit or is remote mounted on the roof or elsewhere outside.
All right, James, I'm going to jump in here again and interrupt you with another poll. If the audience could please answer this question pretty quick. When it comes to fuel type, what type of generator do you specify most? So we're looking for one answer again. Which of these specific fuel types are you working with the most? And we'll give it a couple seconds here for everyone to reply. And oh, I think we have a landslide here. So far the response is 78% of respondents say diesel. And then it looks like about 16% are using natural gas, and then everything else is pretty low. So diesel seems to be the winner here. All right, so we'll turn it over to you, Dana. What's next?
All right. Well, Amara, the results of that poll are definitely not surprising because, as we noted earlier in this presentation, the bulk of the people on this call are designing systems to support critical loads such as hospitals, right? And for these types of facilities, diesel is by far the most popular fuel choice. However, it's not the only kind. So when it comes to types of fuel, we've got many options. We've got diesel, we have natural gas, we have dual fuel, which is a combination of diesel and natural gas, and we even have propane. So diesel, as I mentioned, is the most common for emergency engines because it's very reliable. The advantages of diesel include that it's able to start in 10 seconds as required for those level 1 systems. It provides on-site storage, which is required for hospitals and many other types of facilities. The equipment's typically less expensive than natural gas historically. I mean, anything's out the window right now when it comes to cost, but historically diesel has been less expensive. And they're also really rugged and reliable. They last a long time. They do have some disadvantages though. Diesel fuel must be treated. The fuel has a shelf life, so it has to be treated and maintained in order to maintain that ASTM #2 standard. And it's also not considered very clean burning, not nearly as much as natural gas anyways. So natural gas is actually one of the most efficient fuel types when it comes to generators. The advantages include, you can consider it an unlimited supply because you're connected to your utility company. And depending on the area, it's typically considered a very reliable fuel source as well. And as I mentioned, it's much cleaner burning than diesel. Disadvantages, though, is that historically it's double or triple the first cost of their diesel partners. They also don't really respond well. 100% block loading, their transient response time is definitely not as efficient as diesel. And they're typically physically larger. They also typically take longer to come up to speed. So when you're dealing with level 1 systems and large engines, you don't really have a guarantee that they will be up and running in the required 10 seconds. The dual fuel begins to combine the best of both worlds, right? It's compression ignited engines that run simultaneously on the combustion of both diesel and natural gas. So the generator still maintains the ability to operate on 100% diesel if it's needed, but it also uses the natural gas. An advantage of these types of systems is that it could extend the runtime of the generator because you get two types of fuel. It reduces operational costs because natural gas is cheaper than diesel, and it's cleaner than its diesel-only counterpart. The disadvantages, and it's a major disadvantage here, is the cost. So that is why we're just not seeing it implemented too much into the hospitals. And then propane is similar to diesel. It requires on-site storage, and the propane tanks actually can get very, very large. But it does have some advantages. The fuel doesn't degrade, just like diesel does. They are easy to start and ready to use. They require less maintenance and have lower long-term costs and overall better for the environment. But the advantages, again here, they're typically higher upfront costs. There's fewer trained professionals that know how to work on these systems. They have a shorter lifespan, and they're slightly less efficient of a fuel source. So with that, let's just, oops, I skipped the slide. Sorry about that. Let's just talk, we'll focus on diesel from here on out, since that's really what everybody's looking on. And with diesel, you do have on-site storage. You can have any number of different ways to do that. You have above ground, you have below ground. If you're inside of a building, you typically will have a smaller standalone tank, which is what we refer to as a day tank. The above ground options could be this standalone tank that you see in the photo here, or it could be mounted directly under the generator, and we refer to that as a belly tank. So there's all different types of mountings for that on-site diesel fuel storage. But regardless of whether it's above ground or below ground, you really need to consider the path for the fuel delivery. So the tank has to be accessible by a fuel truck, right? Sometimes you may be forced to put that tank in a fairly inaccessible location, which is okay. It's not great, but it's okay because they do offer remote fill stations. Of course, there's piping associated with it, but it is an option. And then in addition to that delivery, critical facilities such as hospitals really should have contracts with the local suppliers to be on a preferred provider that would meet those additional AHJ requirements for having the ability to obtain fuel as a first priority. When you're talking about diesel, maintenance is a concern. And I'm not talking about your typical preventative maintenance of mechanical components or servicing of equipment. I'm talking about the shelf life of fuel. Diesel has it, and it basically will deteriorate if stored for over 1 year. So when high capacity tanks are used and the fuel isn't necessarily always cycled through, the fuel definitely needs to be periodically drained and replaced with fresh fuel. Of course, that's quite costly. You're not just going to dump the fuel. That's not possible, but they do offer fuel polishing systems that can be used to clean the fuel. Basically, they're removing contaminations such as the water and dirt from the diesel fuel and cycling it back in to freshen it up. Another thing to be aware of on the fuel system side is the possible curtailment arrangements that exist between the facility and natural gas companies. Now, remember, we're talking about diesel here, so I'm not talking about natural gas generators. I'm talking about other users in the system. A key example of that would be if you have a hospital that has dual fuel boilers, where it uses natural gas as a primary source, but diesel as backup. If contracts with the utility company are made, which many times are made outside of the engineering design team's knowledge, that could have an impact on your system. So a curtailment rate allows a utility company to basically restrict the usage of fuel, which the boiler then would use the diesel fuel, eating into that required fuel storage. So taking that into account when you're calculating your runtime and your storage is definitely a requirement. And then, of course, with everything with engineering, there's more and more codes that reside when planning out the fuel system. Both the IBC and the IFC have storage quantity limits when you're dealing with indoor fuel. Specifically, IBC Table 307 limits that storage of Type 2 diesel to only 120 gallons inside of a control area. That's not very much. Now, fortunately, there are footnotes in there that allows this capacity to be increased 100% 2 times. If you have both a fully sprinklered building and the fuel is stored in an approved storage tank, you're allowed up to 360 gallons in the room. And then NFPA 37, as James mentioned, it governs the amount of fuel that can be stored, but the IBC actually has stricter requirements here. So again, you've got to look at all of your codes and what your local jurisdiction is going to require. And then NFPA 110 also has distance limitations that you must maintain from the building. You can't have a fuel source any closer than 5 feet to close to a building. All right, so let's now talk about how we make our generator system future-proof by providing the most flexible and scalable design as possible that fits within our owner's budget. So it requires appropriate space planning, adequate capacity in the distribution systems. So while you're assessing the loads and determining that ultimate redundancy desired, it's really important to understand the ultimate planned growth for a facility. You know, perhaps there's planned expansion on the campus, or maybe they can't afford to put all of their desired loads today, such as large centrifugal chillers. Maybe they can't afford to put those on emergency power right now, but they want to in the future. So you've got to plan for that space and flexibility. A parallel generator system will allow for such flexibility as long as it's thought through at the forefront of the design. So you need to be able to accommodate the varying loads over time. So running not only the load analysis, but the future anticipated load analysis will allow you to properly size your generator plant. And then lastly, I just want to point out that when you are designing for that future flexibility, it's really important to think logistically phasing wise, site logistics, how are you going to get this equipment in? If you're planning for future equipment to go somewhere, how will it get in? What if it fails? How will it be taken out? Are the systems accessible? Can you get to them? You just want to make sure that as you're planning through that, you're thinking through the long-term operation, because when you're putting these systems into a building, you're expecting them to last 30, 35 years. All right, so that really wraps up our presentation today. We hope you've gained a good understanding of the multitude of codes and where they apply, noting that you also really need to pay attention to local requirements. The applications of the systems to support the different occupancies truly matter, and they have an impact on the design. It's important to define the ratings of a generator system, understanding the load profile and ways to mitigate their effect on the generator will inform that overall sizing. Coordination with other disciplines is crucial to the successful generator deployment. So with that, Amara, I will turn it back over to you.
All right, excellent. Thank you so much. Thank you, Dana. Thank you, James. We are now going to move into the question and answer portion. If you'd like to type your question into the Ask a Question box, please type the presenter's name before your question so I know who will answer it. And we'll get to as many questions as time allows. Questions that we don't get to today, we will post online at csemag.com. That's www.csemag.com. And don't forget to download that presentation. To download all these slides, please use the Event Resources tab on the left side of your screen. All right, James, we are going to kick this one off with you. What is alternator pitch, and how does it impact design?
Yeah, so the alternator pitch typically comes in like two flavors, 2/3 pitch and 5/6 pitch. And most installations use the 2/3 pitch, especially in a 4-wire system where you have single phase loads. You'll use the 2/3 pitch, and that's the most commonly used one. But occasionally you'll run into an installation where you've got an older 5/6 pitch generator already installed. And if you're trying to parallel those two, you need to be aware that you could be introducing neutral circulating currents if you don't mitigate those. So you can use something called a neutral current limiting reactor between the two to help mitigate that. So it's just something else to be aware of in your design process.
All right, excellent, thank you. Dana, I'm gonna turn this next question over to you. Do fuel polishers help? And is it frequent that the fuel is bad? How does that work?
Yeah, so great question. Like I mentioned, diesel fuel does have a shelf life. So when it's kept in a cool and dry location, such as a UL listed storage tank, it typically won't last longer than 12 months. It will deteriorate if stored longer than that. So yes, when you have those high capacity tank storage systems, when you're not using a lot of the fuel, you do need to clean the fuel. And a fuel polishing system is basically just a filtration system that it separates out the water, it removes any of the accumulated contaminants, sludge, even algae growth from the fuel. You can have on-site fuel polishing systems where they cycle as needed. But if you don't have a permanent solution in place, there are maintenance providers that will come in and pump out and filter out that fuel for you. It's just really important that the operators of these facilities do understand that, because if you have bad fuel, then your engines aren't going to operate when you really, really need them. So yes, fuel polishing systems, highly recommended.
Okay, good point. Thank you. We're going to stay on the topic of fuel. James, this next question is for you. Are natural gas fuel generators allowed for emergency generators?
Yeah, that's a good question. So it really depends on your jurisdiction. It's the NEC leaves that determination up to the authority having jurisdiction. You have to seek AHJ approval before you can implement a natural gas generator to meet emergency load requirements of NEC Article 700. Okay. And I just wanted to add to that basically the reason why is because natural gas in every location isn't always determined to be a reliable source of fuel. It has to be deemed a reliable source by the authority having jurisdiction.
Sure. Okay. Thank you. Dana, next one's for you. You discussed the effects of high ambient temperature on that generator. Are there concerns in low ambient temperature environments as well?
Yeah, there definitely are. The high temperatures get all the attention, but extreme low temperatures are a concern as well. So again, you have the similar situations with inadequate oxygen levels, which could cause problems in startup. But another problem that could exist is actually the gelling of diesel fuel. So the low temperatures can actually cause diesel fuel to gel and alter the flow characteristics of the fuel, which definitely you don't want, just like the fuel polishing that I talked about. So there are ways that you can have additives added to the fuel to help to eliminate that. You want to definitely winterize your systems to avoid that gelling, and just make sure that you are just taking into account all of the geographic regions in which you may be, because all of them have an impact on your generator system design.
All right, thanks, Dana. James, we have a couple questions here that are related, so I'm going to tell you all what these questions are, and then we'll try to get to those answers. They're all about transfer switches. Some designers prefer manual, some prefer automatic. Why is automatic not the preferred option? And when would you use manual?
Good question. Yeah, so if you have NEC 700 emergency loads or NEC 701 legally required loads, there's a very specific requirement about the duration of outage when the utility fails to when the generator picks up those loads. There's a certain window that's defined. For emergency, it's 10 seconds. In those cases, you need an automatic transfer switch to make that transition in that short duration. If you have optional standby loads, you can put those on a manual transfer because there may be instances where it's of lower priority. And if you have capacity on the generator, you can choose to manually transfer it onto the generator system once all the other ATSs have brought the required loads on board.
Okay. So Dana, I'm going to ask you, this is kind of a follow-up question related to hospitals. So do you need 3 automatic transfer switches, 1 for life safety, 1 for non-life safety, and 1 for fire pumps? Is that required in a hospital, or how does that work?
Well, a hospital does require at least 3 branches of power. It's not exactly what you just said. It's actually for life safety, critical, and equipment is what we call it in a hospital. But it is not only a hospital. It's like what James mentioned. If it is Article 700 emergency systems or 701 legally required, those systems also have to have their own dedicated transfer switches. So you would have a separate fire pump, you would have a separate emergency transfer switch, and you would have a separate optional transfer switch. So it's not just hospitals where you've got to understand that code. It's very well spelled out inside of Article 700 on what else would require different transfer switches.
All right, well, thank you for that clarification. And it looks like we have time for one more question. James, this one is going to go to you. How is the load distributed from one generator to multiple transfer switches?
Yeah, that's a good question. So in the case of one generator and multiple transfer switches, you're going to land into a board of some kind, right? So whether it's a switchboard or a switchgear configuration, but code requires, NFPA 700 requires that you have separate vertical sections serving the the emergency loads, the NFPA 700 emergency loads, your life safety, egress, exit signage, and fire alarm systems. Those type of loads have to have their own dedicated vertical section serving that transfer switch. And then out of a separate section, you can serve both legally required 701 and optional standby out of the same vertical section if you so choose. In most installations, you'll have 3 separate vertical sections serving, those 3 separate branches being emergency, legally required, and optional standby.
All right, very good. Well, I would like to wrap up by now thanking these extraordinary subject matter experts, Dana Jensen and James Lessard, for sharing their extensive knowledge of generators. And I'd also like to thank ASCO for supporting this education session. Before you go, we do need your feedback to improve future education sessions. A couple of questions are about to pop up on your screen, and please take a few seconds to answer these. Finally, on behalf of Consulting Specifying Engineer and CFE Media and Technology, thank you for joining us. We'll see you at the next session. Goodbye.